I'm delighted to be able to present to you some of the work that we do in this NanoElectronics Laboratory at UCT in the Department of Physics. And as you've already heard from Jody, there's lots of exciting work going on in South African Quantum Technology Initiative, and I am a contributor in some small way to this. The title of my talk is Quantized Single Electron Pumping, and the fun part is Electrons Go Surfing. Now, from the title, I'm sure you've gathered already today that the person or the entity of interest, of course, is electrons. And I'm going to go all the way back to the early Greeks, who were the first really that we know of to engage with the concept of charge and electricity. And it was very primitive in those days, where they would be hunting fox, and of course they would collect fox fur. And then they also had access to resin from dried sap from trees. And playing around as with human nature, the experimentalist in all of us, they would rub the fox hair against amber or resin, and they noticed that things would charge up. The resin or the amber would charge, as well as the fox hair. And that was really the first really exposure of the strange entity of electricity. But of course, back in the 12th century BC, no one really knew, of course, what was going on at the time. We jump forward now all the way to the 1600s, where a British or English thinker known as William Gilbert actually started to engage a bit more in depth with the concept of this charging of fur and amber. And he actually coined the phrase, or the term rather, electron. Now, interestingly enough, the word electron actually has its origins in Greek, and actually is the Greek word for amber. So you can see now the link from what the Greeks were playing with in the early 12th century to the development of this idea, this concept of a charge of an entity now in what was then the 1600s. So moving right along, we come all the way now to the end of the 1800s, 1897, and here we have J.J. Thomson. Now, if you've studied physics, even at the undergraduate level, in even a service course at university, I'm sure at some point you would have come across the effects and the experiments of Thomson. He was a physicist who was working at the Cambridge University, slightly the Cavendish Laboratories in the United Kingdom, and he was working on understanding and developing a model of the atom. And here you can see a evacuated tube, and there's an anode and a cathode. And for those of you who are not familiar with that concept, it's just a way of getting electrons to fly from one side to other through a vacuum under a potential difference. And he also had a magnetic field, so he can get to play with these electrons. And so what physicists and scientists at the time were understanding is that you had these charges, and they could be manipulated via magnetic fields and electric fields. And of course, there's the well-known model of the atom known as the plum pudding of the atom. And that was what Thomson came up with in the early 1900s, was that the model of the atom was more like a plum pudding. You had this positively charged matter, and within this positively charged matter, like the raisins, you had electrons. Of course, we know now that this model is completely wrong, but this was the first thinking of the atom, and of course of what actually these electrons are, what this negative charge is. Thomson had a student who was called Ernest Rutherford, and he was also at Cambridge University, and he continued the work of his supervisor, where he came up with the Rutherford model of the atom. So there you can see Thomson's model, which is the plum pudding, but Rutherford came up with quite a different model of the atom. His model was rather that you had the center of this atom, which was a solid core, and then around this electron cloud. So in a sense, Rutherford's model of the atom was really open space with a solid core. You can think of it like our solar system. We have the sun, and orbiting the sun, we have all these planets. And so the experiment that Rutherford carried out, which helped him come up with this model, is demonstrated over here, where you have this radioactive source that's emitting positive charge. And he fires this positive charge at a thin gold film that you can see is placed in the way of the beam of positive charge. Now, what Rutherford expected was, because his model was mainly space, the gaps, he was expecting most of this positive charge to fly through. But what he occasionally found was that some of the positive charge reflected right back in the direction in which it was fired. There's a quote, well-known quote from Rutherford, which goes along the lines as that when he saw this happen, it was as if someone had fired a bullet at a piece of tissue paper and the bullet came flying back. But what you can notice if I replay this again is that around this gold film here, there's a scintillator, which is a detector. And so he can detect how these positive charges are flying back. See, most of them go through over here, but some of them are scattered in all different directions. And some, as you can see, come all the way back. And that's really how the model of the atom developed. And then since then, more pioneering, what would be regarded as classical experiments took place. This is a well-known classical experiment, which I remember doing as an undergraduate student at Wits University, where you were able to determine the charge of an electron. So we're talking about this concept now of an electron, which goes back to the Greeks, coined by Gilbert, discovered by Thomson and electron. And now we're talking about experiments that help us determine the properties of this electron. Bear in mind, even today, with our understanding of quantum mechanics, we don't really know what an electron is, but we're going to get there. So here you can see a little video of the Millikan oil drop experiment, which I think lots of students who are hopefully listening would have come across. The idea is that you have an atomizer of oil drops and you charge them up and you fire them into this region. You can see the charged oil drops there, and they fall under gravity. You can see the oil drops are just simply falling in this space, looking through a little microscope under vacuum. But when you turn on a voltage, you can see you can get these charges to accelerate up. And by balancing the gravitational force pulling them down with the electrostatic force pulling them up, people and even students today were able to determine via a set of basic equations the fundamental charge of an electron. If we move on then, of course, from the Millikan oil drop experiment, of course, everyone has heard of Bohr. And Bohr now is bringing into our classical model of electrons and atoms, a classical, rather quantum mechanical model of the atom. And this is known as the Bohr model of the atom. And here you can see the central core based on Rutherford's model. But around this, electron clouds, which are quantized in their energy. And the electrons can only exist at particular orbits around this nucleus. And this is the foundations of the Bohr model of the atom and the foundations of quantum mechanics. So where we stand now, and as I said, I just wanted to give everybody a very brief history of the electron, because the electron in the concept of the work we do in SAQ-UTI and the quantum work we do is very much the main character. Now, once you've got electrons, as was discovered earlier on, you also realize that there's very interesting properties that are associated with electrons. One of them, of course, is an electric field, and that's because an electron has a charge. If something's got a charge, it produces an electric field. Also manifests itself as a voltage. We know about voltages in our homes, voltage that are required to run our electrical devices. And of course, if you have moving electrons, which we call current, we have magnetic fields, and MRI scanners use them. And what's interesting about these electric fields and magnetic fields, which are created by electrons, electrons can also interact with these fields. So this allows physicists and engineers opportunities to engage with electrons and to probe them with the fields that they create. Now, I want to get into the concept of dimension and what really is an electron, okay? So unfortunately, an electron is so small that quantum mechanically we regard it as a point particle. What that means is that as far as physicists are concerned, an electron doesn't even have dimension. It's so small, you can't even imagine it as a little ball. But in the classical sense, we can, and we can give it a dimension of 5.64 femtometers. Now, femto is 10 to the minus 15 of a meter. So 0.0 and count 15 noughts of a meter. So we're talking small. Now, I don't think the human brain can really get its head around something so small. So I've attempted here to put it into context. Let's take the average size of a human, which is 1.7 meters, and let's consider the diameter of the sun, which is 1.39 billion meters. And now we have our classical size of our electron at 5.64 femtoamps. We can calculate simple ratios. If I calculate the ratio of how much bigger the sun is than the human, in other words, how many humans would have to lie head to toe to reach the diameter of the sun, that comes up with about 365,000. Okay. And no, sorry, I've got the statistics wrong. That gives us a massive number. And if you want to know how small the electron is compared to a human, how many electrons can you stack one after the other to get the same length as a human? Now, it turns out that an electron is 365,000 times smaller than the human compared to the human to the sun. So this is a comparison of how small an electron is. We, of course, are extremely small compared to the sun, but an electron is 365,000 times smaller than that when compared to a human, though that's only on the classical limit. Now, we understand now that electron is extremely small. It's a point particle. And so I'm going to introduce you now very briefly, before I get onto some of the research we do, into some of the quantum mechanical properties of electrons. So here's an experiment that was conducted by Davison and Germer in 1927. And basically, it's an attempt to understand the strange concept of an electron, that it actually behaves like a particle and a wave. And so here you can see a trough of water that's being impinged on a double slit over here. And you can imagine this happening in a pool where you have a wave coming through. It hits these barriers over here, but there's two little holes, and the wave moves through, forming these concentric circles, which interfere with each other constructively and destructively. So if you understand anything about wave mechanics, you know there's a crest of a wave and a trough of a wave. And if they interfere with each other, you can have the formation of crests and trough. And on the detector screen there, you see dark regions and light regions where you have a crest, dark regions where you have a trough. And so that's an interference pattern accordingly for water waves. Now here you can see an electron, single particle, being fired at a double slit as well. Now we know the electron's going to go through either the right slit, or it may have gone through the left slit. But if an electron behaves like a wave, it wouldn't be surprising that it forms the same pattern as water waves. And here you can see the idea behind it. Here you can see a light wave. So we know photons are the quantum nature particle of light, and we know but we also know that light is a water wave, is a wave. Sorry, not water, but it's a wave. So we can fire this electromagnetic wave, light wave, at a double slit, and we get the same kind of interference pattern, or constructive, destructive interference, as you would see from water wave, because light is a wave. If we had, say, a bucket full of sand, and you poured the sand over these two double slit holes over here, you would expect two piles to form, no interference. The sand particles will either go through the left or go through the right. Equally so, if you fire single electrons at a double slit and you consider them as particles, they would behave via the sand, where they go through either one or the other. In this case, they're going through all the other, and they appear in the center. Now, what happens if you consider the electrons to be waves? Well, if you consider the electrons to be waves and you fire a whole lot of electrons through a double slit, what you find with your detector is the electrons, which we know are point particles, form exactly the same kind of interference as these light waves or even the water waves. But here's where it gets crazy, because if you do this experiment, the exact experiment is done over here, but instead you also monitor which slit it's going through, then suddenly you get a pattern like this, where either it goes through the top slit or it goes through the bottom slit based on your detection here. So what you're looking at is quantum craziness. You're looking at the fact that the same experiment produces different results depending on how you're observing the experiment. If you're just observing the detector here, the results will appear like a wave. If you're observing the detector here as well as the slits, then the result will appear as a particle system. And that is the craziness of quantum mechanics. Of course, there were lots of experiments that were done after this to play around with quantum mechanical properties. And here we have something known as the Stern-Gerlach experiment, which was an empirical investigation into something known as quantum spin. Now, mathematically, you can think of spin of an electron like the Earth rotating on its own axis. But of course, the Earth cannot rotate on its own axis. An electron cannot rotate on its own axis, because an electron doesn't have dimension. So how can something that's dimensionless actually rotate? So there's this quantum mechanical property of spin, which we call spin up or spin down. And you can see, if based on this little video over here, if it's spin up, the electron will go in one direction. And if it's spin down, the electron will go in another direction when it's exposed to a magnetic field. But the reality is, we don't really know what electron spin is. I said to you, mathematically, you can imagine it like the Earth rotating, spinning on its own axis, or a spinning top. However, it can't actually spin like that because it doesn't have dimension. So I normally tell my students when I lecture in quantum mechanics at UCT, I say, imagine you have a person who's born blind. So I've got it here, the tale of a blind man, 2 tiles in a desert. A person who's born blind has no concept of color. They don't know what green is, they don't know what blue is, but more importantly, they don't even know what black and white is. And you take this person for a walk in the desert, and you come across 2 roof tiles that are sitting in the desert sun. You, as the person who can see, notice one tile is black and the other tile is white. This blind person can't see the tiles, has no concept of color. You take the person's hand and you place it on the black tile, and you say to him, oh, that, and he says, oh, that feels hot to the touch. And you say, yes, it is. That's a black tile. Then you take the person's hand and you ask them to touch the white tile, and he will feel, or she will feel, that that tile is cold. So the person will understand that a black tile will be hot in the sun and a white tile will be cool in the sun. But the person still does not understand what black and white is and can't even imagine it. And that's, I think, where we stand with the concept of spin. We know there's this quantum mechanical called spin. We know if it's spin up, it behaves in one way. If it's spin down, it behaves in another way. But don't think anybody knows really what spin is. No one does. And if they claim they do, then they really don't. So what I'm going to talk to you a bit about now is how we can now play with these electrons. We understand the electrons now to some extent. We've moved on from a classical understanding of electrons. And now it's our opportunity to engage with them and see what exciting applications we can use with electrons. Now, here is something known as the quantum Hall effect. Now, if you're a physics student, you may have studied the Hall effect in undergraduate physics. And really, it's understanding how electrons behave when moving in a magnetic field. So if you have even a semiconductor or a metal, and you have a magnetic field pointing out the page, and you allow electrons to move along this direction here, you see the current arrow coming here. As they enter this region of the magnetic field, they'll experience a force. It's called the Lorentz force. The same way the electrons here were experiencing a force getting them to bend up or bend down because of this magnetic field. This magnetic field here is going to cause these electrons to bend. And in this case, you can see the force is calling them to bend up over here. And so you get a collection of negative charge here. As the electrons enter, they get bent up and you have a negative charge. Now, you also know from physics, if you have a negative charge here and a positive charge here, you're going to create a voltage drop across here. And that is known as the Hall voltage. And what's interesting is a function of magnetic field. If you increase this magnetic field, the Hall voltage, which is shown here by rho xy, is just linear. And the voltage longitudinally, if you measure that, just remains constant. Now let's introduce a quantum mechanical world. And here we introduce a quantum mechanical world where we have something known as a 2-dimensional electron gas, and I'll explain to you that later on. Now, if you have electrons that are no longer free to move in 3 dimensions, but rather they act on a plane, like snooker, on a snooker balls on a snooker table. If you play a game of snooker or pool, you know that's a 2-dimensional game. The balls, you don't play snooker in 3 dimensions. And if you now take these electrons in 2 dimensions and you carry out the exact same experiment, look what happens to this red line. It's no longer constant, like in the case of the classical. It forms these very interesting quantized steps. And the constant line over here, which is the longitudinal voltage, is no longer constant. It forms these very interesting oscillations. And this is known as the quantum Hall effect. And it's quantum mechanics that can explain what's happening here. And it's this phenomena which is what we use for a standard for electrical resistance. So when someone tells you that something is 10 ohms or 50 ohms, it's been calibrated against the formation of these resistance lines over here based on quantum mechanics. I'm not going to go into the detail of the quantum Hall effect. That's a topic for another lecture, but just an opportunity to show you that very interesting quantum mechanical effect when you move from the classical to the quantum is actively used today to standardize resistance around the world. We have a standard of resistance in Pretoria, in Nemisa, which is used to calibrate all our instruments that require an accurate measurement of resistance. I'm now going to take the next few minutes to mention some of the more exciting work now that you have a good understanding of electrons and where they come from on the NanoElectronics Research Laboratory at UCT, and some of the work we're doing in collaboration and with generous support and funding from the South African Quantum Initiative. So one of the things we're most proud of in our NanoElectronics lab at UCT is we claim to hold the coldest place in Africa. What we have here is a a dilution refrigerant, which has a base temperature of 7 millikelvin. And so when you're trying to control and manipulate single electrons, you have to be able to cool them down to really low temperatures. Because you can imagine if you have a boiling pot of water and you're trying to trap a molecule of water with a tweezer, if the water's bubbling around on a pot, it's much harder to trap than if it's cold and still and basically frozen. So we try to cool our electrons as cold as possible, and we take them down to around 7 millikelvin if possible. Bear in mind that on the Kelvin scale, the coldest known naturally occurring place in the universe is the Boomerang Nebula, this beautiful nebula here shown, and that is 1 Kelvin. That's the coldest known naturally occurring place. Our fridge goes down to 7 millikelvin, so that's 7/1000th of a degree above absolute zero. Now, of course, there's other places on the planet that can achieve lower temperatures, and even you can have single atoms at lower temperatures. But this, I claim, is the coldest place, at least in Africa, where you can make use of that temperature to cool secondary things. So how do we create this two-dimensional electron gas I was talking to you about earlier on? How do we create our electrons to act like snooker balls on a snooker table? And this is known as molecular beam epitaxy, where you can grow a semiconductor material in such a way that you can bend what's known as the conduction bands, if you've studied some semiconductor, in such a way that 90 nanometers below the surface, you create a quantum box. So you basically create a box, and all the electrons fall into this box, and they sit in a single energy level, and they become what's known as a two-dimensional electron gas. If you cool them down, the electrons will collect in this box over here, 90 nanometers below the surface, and they'll remain in a two-dimensional plane. And now you have a very interesting quantum system. And once you've got this two-dimensional electron gas system, you can begin to play with the material by working in clean rooms and making use of semiconductor clean room fabrication techniques, which is a combination of electron beam lithography and optical lithography. And you can start to make nanostructures in this material. Here is a nanostructure called an electron pump, and I've scaled it to the size of a blood cell. So each one of these gates over here are about 100 nanometers in diameter. In width over here, from here to here, is about 100 nanometers. That's about the size of the coronavirus, to give you an idea. And these are made using electron beam lithography and evaporation techniques. This material here is actually titanium gold, and these are known as finger gates. And if you apply voltages to these gates, you can create what's known as a quantum dot. And this is how you can get electrons to go surfing. So here you can see we have our device. You can see we have a nanowire, which we've etched there. So we no longer have a two-dimensional electron gas. We've restricted the electrons into this very narrow wire here so that they can move only in one dimension, like soldiers marching across a bridge. And then we can apply voltages to these gates, the left gate, the middle gate, and the right gate. Now, of course, you know an electron is negatively charged. So if an electron sees a negative voltage, what it's going to see is a potential hill. If it sees a positive voltage in the middle gate, it'll see a valley. And if you have a right gate again with the negative voltage, it'll see a potential hill. And so what you can do is you can oscillate these barriers from negative to positive, and you can get this electrostatic potential profile to oscillate up and down. And so you can get electrons to tunnel in and to tunnel out. So it's really like electrons going for a ride on a wave. They come in and they go out. And you can control how many go in and how many come out. So you end up having what's known as an on-demand source of single electrons. Here's some publication work that we did where you can see the electrons come in. You can control how many stay in. You can then raise this barrier up, and you can inject one of them, keeping the other in. And so now you have an on-demand source of single electrons. And so we can provide you with 3 electrons per cycle, 4 electrons, or 1 electron. You can trap 5 electrons. You can send 3 out and keep 2. So we're starting to play with these electrons, which, bear in mind, don't even have dimension. They are so small. But nevertheless, we have the ability to control them. And here you can see a little video where we're actually just using 2 gates to pick up and shuttle as many electrons we want, one at a time, across. And we can do this 180 million times a second. Okay, so here's just some data. I'm not going to go into the detail now because of time, but you can see that we have the ability to control and manipulate single electrons. And then, of course, we can play with magnetic fields. We've now got these electrons. We can turn on the magnetic fields. As I said, electrons interact with magnetic fields, and we can see how electrons behave in magnetic fields. And this actually starts to then lead us towards some interesting quantum applications. But a current standard. So, for example, I mentioned the quantum resistance Hall standard. This is a standard metrological standard. But what about current? At the moment, there's no standalone current standard. What is the basic definition of current? Charge per unit time. So if we can move electrons in a controlled way, and we know exactly how many electrons we're moving, we have an exact current standard which would calibrate our instruments. That's something we're working on. And with magnetic fields, you can actually control the accuracy of the pumped electrons. You can see here different what's called pump maps. Each time you see a white region here, you've got very stable electron transport. Here you're moving 1 electron per cycle, here 2 electrons per cycle, here 3, 4. Here you're picking up 2 electrons and pumping 2, but here you're picking up 2 and pumping 1. Here you're picking up 3, pumping 3. Here you're picking up 3 only and pumping 2. What I mean by pumping 2 is you're ejecting 2, keeping 1. Here you're actually ejecting 1, keeping 2. And so it's a pump map that tells you how many electrons would you like? How many would you like to keep? And as you increase the magnetic field, it becomes more accurate, more stable, and becomes more in line with the current standard. Quickly, I'll show you this before I get into the last slides. Here I'll show you how the pumped current, here you have 1 electron per cycle, 2 electrons per cycle. But as you change on this axis over here, the magnetic field, you can see how the pumped current behaves in very interesting oscillatory behaviors. And what's very interesting is if you keep going, you can enter a really stable region where here you're really controlling 1 electron per cycle, very accurately, very stable. And this is the building blocks of a current standard. Something else you could do with electrons is you don't even have to study them in solids. You can also study them on superfluid helium. So if you take helium gas and you cool it down to a liquid at around 4 Kelvin, and then you cool it even further, as is shown in this video over here, it becomes a superfluid, perfectly calm. It's got 0 viscosity, so it'll creep up and you'll actually see it'll leak. If you look here, here's a container that's sealed at the bottom, and they fill it with liquid helium, and then they cool it. It's not leaking through the bottom, but as it becomes superfluid, you can see it starts to leak at the bottom. And you can use this as a way of controlling electrons. What you do is you get electrons via a tungsten light bulb to land on the surface of the helium liquid, and then you can control the electrons on the surface, like you would balls floating, like these colored balls that children play with. Imagine they were charged and you had them sitting on a perfectly still pond. You can move them around on the pond. One can do that. And at UCT, we've built a cell like this that allows us to control electrons on superfluid helium, and we've got PhD students working on this. Now, very briefly, the 2 quantum applications for the second quantum revolution that we're looking at, of course, is a quantum metrological standard of electrons, which I told you before. But the other work, very briefly in my last 2 minutes, is, of course, quantum spin selection. Now, there were some interesting questions asked about why isn't South Africa building a quantum computer? And I think Jody answered that question pretty well, in the sense that we're not trying to build a quantum computer for many reasons. But that does not mean we shouldn't be participating in the technology behind, at least in my opinion, quantum computing. So some of the work we're doing at UCT is not to build an entire quantum computer, but to investigate different technologies that will be incorporated into quantum computing. Because in South Africa, at some point, we're going to have to build or buy, manage, operate our own quantum computers. And we need to be active participants in understanding the technology, in some way contributing. So the work I'm looking at with quantum spin and single electron pumps is if you get hold of an interesting 2-dimensional electron gas material, there's something that electrons have which is known as spin-orbit coupling. Now, if we think about an electron classically again, we can think about its spin as a rotating on its own axis, like the Earth on its own axis. And then we can think of the electron orbiting the nucleus of the atom like the Earth orbits the sun. And so you've got 2 spins. You've got the orbit and you've got the spin. Now, electron behaves the same way, but because the electron is charged, and as discussed earlier, anything that's got charge that moves produces a magnetic field. So what happens with an electron, it can interact with its own magnetic field. It's producing a magnetic field from its spin, and it's producing a magnetic field from its orbit. And those magnetic fields can interact with each other, and that then allows the spin of the electrons to be manipulated. They come out with a certain spin orientation, and we can produce an electron pump where we deliver individual electrons, and then we can start to manipulate their spin using these gates over here, and we can have gates here to select The gates allow us to flip the spin from up or down. These split gates over here with the gap allow us to select different spins up or down. And so here we have the building block of a qubit. And this is a project that's currently being funded by South African Quantum Initiative. And we are delighted to be working in the space and advancing quantum technology in South Africa. So thank you very much for your time. I see 30 minutes is exactly up, and I appreciate the opportunity to speak here, and I hope it was of general interest to the wider audience in attendance. Thank you very much.